Hey, what's up, guys? This is Cheng here again. So let's take a look at today's daily challenge problem number 858, mirror reflection. I mean, this is more like I would say it's like more like a math problem, but let's just take a look. There's a special square room with mirrors on each of the four walls, except for the southwest corner, which is the bottom left corner. And there are like receptors on the remaining corners numbered from 0, 1 and 0, 1 and 2. So as you guys and a beam and there's a laser ray from the bottom left corner. First it will first meet the wall at the distance of the east wall at distance of Q, something like this, right? And then it asks you to return the num which receptor the ray will meet first, and it's guaranteed that the ray will meet a receptor eventually. So for example, right, we have a so the laser always starts from the bottom left corners, and then it will always hit the east wall first with like a distance with the distance from 0 to Q, right? So this is a Q, and then the length of the square is P, and I just ask you which receptor it will meet first. So for example, we have 0, 1, and 2. So for this one, right, I mean the first receptor it will meet is 2 here. And then there's a P is a 1000, and the Q is like always equal or smaller than the P. Okay, so let's draw some examples here, right? I mean this is actually the first one is always the easy one. Let's try to see when it will reach the receptor 2 here, right? So so the first one is just like this, right? I mean this is receptor 2, 1 and 0, and this is P, this is Q. So this way we can reach the receptor 2, right? And we can another way is like this, right? We can do this, and then basically we reflect it like 4 times, right? 1, 2, 3, 4, and then we reach 2 here. And how many Qs we have here? We have one. So we have a 1 Q, and then we have 2 Q, 3 Q, and 4 Qs here. And then, so the first observation is that, as long as the Q is an even number, the number of Qs is even, we know it will definitely reach the receptor 2 here. All right, so that's the observation. And let's take a look at a more difficult one. So then how about the receptor 0 and 1, right? So for those ones, we have to draw some like different squares here. Let's say we have this one. Mm, let's say the length of P is 3, and then the Q is 2. How about this, right? So the Q is 2, which means something like this, right? So the laser will first reach this 2 here, and then it will reflect to here, right? When it reflect to here, if we're only checking this one square, it will go down and somewhere go back here, right? But that will make it harder for us to I mean to observe. So what we can do is we can extend this square by 1 here. So which means that since this thing will reflect to this side first, right? So this will identical to what? To this line here, right? And then This one will go to here, right? And just like this one will go back to here, right? As you guys can see here, so actually we're transforming the problems within one square into two squares now, right? And now, as you guys can see here, so this one, so this time the receptor is 0. So yeah, this is 0 in this case. So when it is 0, what do we have here? So we already know that. So how many queues do we have? We have 1 queue, 2 queue, and 3 queue, right? And so then the second observation we have here is that, as long as the number of queues is odd numbers, then we know it will either reach the receptor 1 or reach receptor 0. And to get how many queues we have here is that, so as you guys can see here, so actually we are trying to calculate, like, we have a p here, right? So there's a p here. How many p's we have? We have 2 p's, and we have three queues. So essentially what we're trying to calculate is that we're trying to calculate the p times m equals to q times n. It means that we need basically how many p's and how many q's will make them even. And when they're even, then it means that, I mean, the the laser has reached one of the receptors, either on the left side or on the right side, right? Because when they reach the same, when they are the same, it means that, the laser has reached one of those two corners, right? And by the time those two, the p times m and the q times n are the same, then check we can check which receptor it has reached, right? So okay, so like I said, when if the q if n is odd, sorry, is even, right? We know it must reach the receptor 2, right? We return 2. Else, I mean, if n is odd, based on how many queues we have, right? Then we know, okay, it may reach the receptor 0 or 1, because in this case, the ones we're drawing here, the the m is odd, sorry, is even. So the m, because we have two m here, right? And m's even. When the m's even, then we know, okay, based on this like trajectory here, we're reaching the what? We're reaching 0 here, because as you guys can see here, so we're going this way and then go up, and then we're going down and down. So that's why we're reaching 0. So another scenario is that, we have 1 here, and another scenario is that like this. So we have 1, 2, and 3. So in this case, as you guys can see, we are reaching the number 1, the receptor 1 here. So in this case, we have one p, and we have 3 queues here, right? We have 3 queues. So which means that when m is even, right, and then we know, okay, it's 0, and when m is odd, then we know it's 1. That's the conditions here. Now the only question is, how can we calculate this m and n here, right? So to calculate that, let me try to start coding here. It's just similar like as what we calculate the GCD, which is the greatest common divider. So we do this while while P times M is not equal to the Q times N, right? Because we're starting from 1 for both M and N here. And then we increase the N plot by 1, and then we M equals to the what? The Q times N divided by P, right? That's how we try to get close to this P and the Q here. We will eventually get the answer here, and the answer has to be an integer. So why is that? Because it doesn't really matter, as even for like 13 and 2, right? I mean, we can always get the answer by what? By this times 2 and 2 times 13. We can always get that, right? That's why it's guaranteed that we have an integer answer for both the m and n here. And then the way we're calculating is we're trying to increase the n's because the n should always be greater than m, right? Because q is smaller than p. That's why we try to increase the n here. Every time we increase the n here, we're trying to get the m by doing this, right? And now once we have the m and n here, we can simply check. Basically, the first thing, if the n is even, right? So when it's even, we know, okay, we return 2, right? We return this receptor. Else if, right? Else if Else if means that n is odd, and then we check if the m is even or not. So if the m is even, we return 1, right? So 1 is this one. And else, the last one is else. Else m is odd. When m is odd, then we return 1. So we return 0. Yeah. So I think that's it. All right. Run the code. All right. Cool. Submit. Yeah. So accept it. I mean, oh, and time complexity, right? So I think the time complexity will be something. The only time we are spending here is trying to get this m and n here, and we have a p to 1000. So this thing is, I think the time complexity is similar like the time complexity to get the GCD, which is the O of log p, right? Yeah. All right. I think cool. I think that's it for this problem. It I know why it got a lot of downvotes because this is like more like a math problem. Hmm. I don't think it's very likely you will get this kind of problem in the interview, but it's always fun, to take a look at this kind of math problem. And I think that's it. All right, cool guys. I'll just stop here. Thank you so much for watching this video and stay tuned. See you guys soon. Bye bye.